All right, guys, I want to show you in this video how we can analytically evaluate a limit using a technique called rationalizing. So let's quickly review kind of this idea of irrational numbers and how we rationalize them. So perhaps you recall, if you look at the number 2 over root 3, years ago, we as mathematicians said if we're going to divide through by a number, let it be rational. So an irrational number, like this number root 3, we don't like those in the bottom. So what we have to do is multiply that number by some form of 1. That is going to remove that square root, that irrational number in the bottom. And the value of 1 we choose is root 3 over itself, because what happens is root 3 times root 3 in the bottom gives us 3. And what we've done is we've taken that denominator, which was irrational, and rationalized it. Okay? Those ratios are equivalent, but now the irrational number, the root, the radical 3, is on top, okay, which is where we prefer it. Okay. Now, if we had something that looks like this, we would rationalize that ratio using what's called the conjugate of the denominator. And the conjugate over itself is going to be not root 3 minus 1, but root 3 plus 1. Because what happens is on top, we're just going to distribute that 2. That ain't no thing but a chicken wing. And on the bottom, what we have is we kind of have this format, a minus b times a plus b, which we all know is a squared minus b squared. Now what's nice about a squared, a being root 3, we just get 3. Minus b, our b term is 1 squared, which is also 1. So long story short, we have two, oops, get rid of this for you. When we simplify that ratio, we get 2 root 3 plus 2 all over 3 minus 1, which is 2. And then we could pull a 2 out of everything, which really isn't the point of this. The point is we have now rationalized what was an irrational denominator. Equivalent form, but now the radical is on top. Okay? So, that said, let's look at an analytic limit for which we might be able to utilize this process. So I'll give you an example. It's a limit as x is going to 0 of root x plus 1 minus 1 all over x. Now, we're looking at that limit, and I'm saying, okay, as we would normally try to do first, I'm going to try and start by plugging in or substituting that 0. So when I substitute a 0 in for this top x and the bottom x, I end up with on top with 1 minus 1, which is 0 over that. Oh boy, there's that indeterminate form. Now remember, that indeterminate form means this, but it also means we might have some more work to do, so there actually is going to be a limit, and this is an example where that's the case. So right now I know that there's probably going to be a limit. I just have to figure out how to find it. So now cue up our rationalizing discussion, and I'm going to multiply the top and bottom by the conjugate of the top. And by doing so, I'm going to rationalize the numerator, even at the expense of making the denominator yucky. So I have root x plus 1 minus 1. Taking the conjugate of that, which is root x plus 1 plus 1. Right? The conjugates, this has a minus here, this has a plus there. And we have a plus b, a minus b over itself. So that's really multiplying by 1. Okay? Now what I'm going to do is I'm going to perform a little magic, a little algebra. Okay? On top, I have a minus b times a plus b. And we know from some algebra 1 that that's going to be a, which is root x plus 1 squared, which is just root x plus 1, minus b, and our b is 1 squared. Okay, so when I expand the numerator, numerator times numerator, those conjugates, I really end up with a nice, easy expression. Okay? In fact, I just end up with x. On the bottom, I'm not going to expand all this mess because I have a feeling that something is going to clean up. And it will. I just bring that denominator down. I'm not going to expand the denominator. Okay, because what's going to happen now is that x on top is going to cancel with that x on bottom. Okay, which means now if I were to rewrite the limit I'm evaluating as x is going to 0, really on top, all I have is 1 now. And on bottom, all I have is this orange part of the denominator, which was the conjugate of root x plus 1 minus 1. Okay. Now I'm going to zoom out a little bit, give myself a little more room. No, it's not letting me do that. Try it again. Zoom out. Oops, it's too far out. And what I can do now that I was not able to do before is substitute that 0 in, right? So the idea is when we can't substitute at first to evaluate a limit, or when we get 0 over 0, when we do substitute, more importantly, which is indeterminate, but it also means there's probably going to be a limit, what I need to do is figure out how to work it so I can substitute. In this case, I work it by using the conjugate. I make the numerator rational of my expression. I rationalize the numerator at the expense of making the denominator irrational. Because what I know for these carefully engineered problems is that ultimately here at the last step, after I simplified all that mess, I can then substitute that 0 in this case in. So now I'm going to substitute that 0 in for x. So I get root 0 plus 1 plus another 1. So I end up with 1/2. Okay? So that technique is called rationalizing the numerator. I multiply by the conjugate of that irrational numerator over itself, which makes a numerator, in this case 1, when I simplify and clean everything up. And even though it makes the denominator messy, what happens is I get to get rid of these x's. I get to cancel out that which was preventing me from substituting in the first place. Okay? So this technique is called rationalizing. And for root-containing limit problems, for which we get 0 over 0 when we substitute, this is usually helpful. All right? Hope you enjoy this. See you tomorrow.